Hi guys. So in this video, I'll show you a theorem. The theorem actually has two parts to it. In this video, I'll only show you the theorem, the first part of the theorem and the proof for that part. And in the next video, I'll show you the second part of the theorem. Now, most of you might have heard, like if you've already taken some analysis course, most of you might have already heard that infinite sums are not commutative. So for example, finite sums, if you're adding up a finite number of terms, like let's say 1 plus 2 plus 3, it's equal to 3 plus 2 plus 1, and doesn't matter in what order you're summing up the terms, you're always going to get the same answer. Now, this is not true in general. If you are, well, it's true for finite number of terms, but it's not true for an infinite number of terms. So let's say you have the summation from n equals 1 to infinity of a's of n, which is of course equal to a's of 1 plus a's of 2 plus a's of 3 plus so on. And if this adds up to x, then another way of summing the same sequence up is to sum up all the odd terms first and then sum up all the even terms, and this adds up to y. So clearly in this case x is not equal to, assuming that x is not equal to y, what we get is that both terms or the same sequence or the same series added up in different order is going to produce different values. So why does this happen? What's happening over here? What's the like the proof? What's the mathematical idea behind it? And that is what I'm going to show you today. The first part, at least half of what's happening over here, I'm going to show you today. But the first thing we are going to the first thing I'm going to show you today is that there are certain infinite sums that are commutative. So when we say that infinite sums are not commutative, this is not true in general. There are some infinite sums that are commutative, but not all infinite sums are commutative. So in this case, in the first part of the theorem is called the Riemann's rearrangement theorem. The first part of the theorem deals with the sums, the infinite sums that are commutative, and then the second part, and probably the more astonishing part, because the theorem is just mind-blowing. The second part of the theorem, I mean, once you read that theorem, you're like, what's going on over here? But the first part of the theorem, it just deals with this idea about that there are certain infinite sums that are commutative. So let's just go ahead and read what the first part of the theorem is. It says that S be any real number. So we know that S is a real number. And it says that the summation from n equals 1 to infinity of a's of n be an absolutely convergent series. So it's an absolutely convergent series. What does it mean by absolutely convergent? It basically means that the summation from n equals 1 to infinity of the absolute value of a's of n is less than infinity. In other words, this series converges in absolute value as well. And then you assume that now the theorem assumes that the because I mean this converges, so it has to converge to a, this series converges, so it has to converge to a specific value. So what the theorem says is, let's assume that the value that the series converges to is s. Okay, this is the probably the more difficult part. It says then, for every function, for every bijective function that maps from the set of natural numbers to the set of natural numbers, the summation from n equals 1 to infinity of a with the subscript alpha n, where alpha is the function, is equal to s. So let me just quickly explain what this part over here says. This notation over here is just a fancy way of saying for any rearrangement of the set of natural numbers, the summation from n equals 1 to infinity of a will remain the same. In other words, no matter in what order I sum up the sum up the terms of the sequence, I will always get the same number s, where s is the real number that the original series converged to. So there is one question, there is one idea that I would like to address. For some of you who already know what this terminology means, I would like to emphasize why this has to be a bijective function, otherwise this will not work. So if a function is bijective, it ensures that it satisfies two other conditions. It has to be injective and it has to be surjective. So surjectivity means that every term in the range of the function is mapped to. The range of the function is the set of natural numbers. So in this case, this ensures that the function maps to all the natural numbers that appear in that appear in the set of natural numbers. And it also has to be injective, because injective basically means one to one. So that ensures that each element of the set of natural numbers is mapped to exactly one element of the set of natural numbers. So these two properties together ensure that when we have rearranged, that when we are adding up the the terms in some rearranged order, we are adding up all the terms, all the terms, all the terms, and we are adding up each term. We are adding each term exactly once. So I mean, the best way to think about it is, let's say that you have a finite number of let's say that you have a finite number of terms. Let's say that you have terms from 1 to 100, and let's say you're adding them. Let's say that you're adding these terms up. Now, if it's surjective, so you have 1, 2, 3, 4, 5. So you have ace of 1, ace of 2, ace of 3, ace of 4, all the way up to ace of 100. Now, if you rearrange these terms and you add them up in some other manner, the two things you need to ensure is that, number one, you are adding up all the terms, and number two, you are adding up each term exactly once. Alpha over here, being a bijective function, ensures that you are adding up all the terms and that you are adding up each term exactly once, so that these two factors are not the factors which are going to change up the sum of the series. Okay, so this is why you want alpha to be a bijection. So now, once again, I would ask you to pause the video and see if you can write a proof for this theorem on your own. This isn't an easy proof. It might take you quite some time to get a hold of what you are going to be doing over here. But yeah, it never hurts to give it a try. So by now, I hope you've attempted this question on your own. Now, I'm going to present a proof. There are different ways to prove it. I personally found this way to be the most elegant method. So I'm going to just use this one. So first of all, I always like to, whenever I begin my proofs, I always like to redefine any variable that I'll be using, or any terms that I'll be using in my proof. So the first thing, I'm going to define s, because I'll be using s. So let s be any real number. Of course, I'll be using the series, so n equals 1 to infinity of ace of n. Be an absolutely convergent series. So I'll state that I'm assuming that it's any absolutely convergent series. Absolutely convergent series. Such that, so I have to assume such that the summation from n equals 1 to infinity of ace of n is s. So I'm just restating these two things over here. And what I want to show that for any rearrangement of the set of natural numbers, of course I'm going to state where alpha is bijective, I have that the summation from n equals 1 to infinity of ace of alpha n is equal to s. Okay. So now I'll begin my proof. So first of all, I'll state that let epsilon be anything greater than 0. You'll see why I need to state this in a minute. Now, notice that since the summation from n equals 1 to infinity of ace of n converges, and we have something stronger that it converges absolutely, but we do not need that that absolute convergence just yet. But since this converges by the necessary convergence test, we know that limit as n approaches infinity of ace of n must be equal to 0. That just follows from the necessary convergence test. Or in other words, if you write out the epsilon delta definition for this, you get that for every epsilon greater than 0, there exists an n naught in the set of natural numbers, such that for all n in the set of natural numbers, if n is greater than or equal to n naught, then the absolute value of ace of n is less than epsilon. In other words, what I'm saying over here is that for any real number you give me, that is greater than 0, I can find some cutoff some cut of n naught such that every number, such that for any number greater than that, so let's say that the cutoff is 2, then ace of 3, comma ace of 4, comma ace of 5, and so on, all of these terms are individually less than the number that you gave me. So if you give me, let's say, just to give you an example, let's say that ace of n is 1 over n, 1 over n. And let's say you tell me that epsilon is equal to 1. So you ask me, well, give me some cutoff such that every term in the sequence is less than 1. So the cutoff will be 1. Well, n naught over here will be 2. Because if you just pick n to be 1, you'll get 1. But then if you pick n to be anything greater than 1, every term will be less than 1. And this is exactly what it's saying. This is saying that for any positive real number you give me, there is always a cutoff such that every term in the sequence ace of n that comes after that cutoff is less than the real number you give me. And what this allows me to say, is the following, that there must also exist a number in the set of natural numbers such that the summation from n equals r plus 1 to infinity of the absolute value of ace of n is less than epsilon over 2. Why is this true? Because we know that the series is convergent, right? So we know that it adds up to a certain value. So let's say it adds up to 6, right? And let's say I want over here, let's say epsilon is 1. So I want the summation from n equals r plus 1 to infinity of the absolute value of ace of n to be less than 1/2. Okay, I know it adds up to 6. We're assuming it adds up to 6, but I want some cutoff such that once I start adding them up, once I add up the terms that are greater than that cutoff, the answer is less than epsilon over 2. Okay, how do I do that? I know that the first few terms of the sequence have to be big. So they have to be big, or they are relatively bigger, but at the end they have to approach 0. They have to become very, very, very small. Why is that? Because of the necessary convergence test. We know that since the series converges, the limit as n approaches infinity of ace of n has to be 0. So what I'm going to do is I'm going to remove the first finitely many terms, so some cutoff over here, some finitely many terms, such that their sum is greater than 5.5. So if their sum is greater than 5.5, then I can sum up the remaining terms, since I know that the sum of all the terms is 6, and the sum of the first few terms is, well, 5.5, or something greater than 5.5, then the sum of the remaining terms must be less than 1/2, because in this case I'm saying that epsilon is 1, so then it will be less than 1/2. So this is always possible to do. It's always possible for to pick such a number in the set of natural numbers, such that if I sum this up, I can always ensure that I'm less than epsilon over 2, where epsilon is any real number. Okay. Next, I'll pick a p. So I'll pick a p that is greater than or equal to this r, such that ace of 1, comma ace of 2, all the way up to ace of r appear in ace of alpha 1, comma ace of alpha 2, comma all the way up to ace of alpha p. Now, why I'm exactly doing this will become very, very clear in the very next step I do. But first of all, I want to tell you why this is possible to do, and this is why over here alpha had to be a bijective function. Now, first of all, since alpha is bijective, we know that there exists some p such that all of these first finitely many r terms are mapped to. Since, well, alpha is a bijective function, it maps to all the natural numbers, so it must map to the first r natural numbers as well. So that's the first thing. There we can find a p such that it maps to the first r natural numbers. Now, one other thing. Why does this p have to be greater than or equal to r? Well, because let's say that the function that we pick alpha is just x. Alpha of n is n. Well, if this is the case, then we haven't rearranged the sequence at all. Alpha of 1 is equal to 1, alpha of 2 is equal to 2, and so on. Now, if this is the case, then it will take exactly r terms, exactly r P will be equal to R, it will take exactly R terms to create the first R terms again. But if this is not the case, let's say I'm picking up, I'm summing up the some let's say I'm summing up the 100, the first 100 even numbers, then this first 100 odd numbers, then the first 100 even numbers again, then the first 100 odd numbers, and so on. Then it will take exactly 2R terms or something greater than R to produce the first R terms. And that's the idea. You can never produce the first R terms by picking less than R terms, by picking something that is less than R. So P over here has to be greater than or equal to R. Okay, and of course this is possible. You should state this. This is possible as alpha, or sorry, as as alpha is a bijection, or is a bijective function. I'm just going to say it's a bijection. Okay. Now I'm gonna say let P, small p, be anything that is greater than or equal to capital P. And now by the triangular inequality, and this is where it will all become clear. By the triangular inequality, the following holds, and this is absolutely amazing over here. Let's look at the summation from n equals 1 to p, where p is anything greater than or equal to p, so it can be anything, as long as it's greater than this p, of ace of alpha n minus s. So let's look at this part over here. Let's see what this is equal to. So first of all, this is equal to the absolute value of the sum from n equals 1 to infinity of, sorry, from n equals 1 to p of ace of alpha n minus, we'll see this, the summation from n equals 1 to r of the absolute value of ace of n plus the summation from n equals 1 to r of the absolute value of ace of n minus s. So notice I haven't done anything. I can just pretty much cancel this out right now. They are the same thing being added and being subtracted, so it doesn't matter. But what I'm going to do is I'm going to group these up. Now by the triangular inequality, this must be less than or equal to the absolute value of the first part from n equals 1 to p of ace of alpha n minus the sum from n equals 1 to r of the absolute value of ace of n plus the sum from n equals 1 to p of ace of n, the absolute value of ace of n, minus s. So this has to be true. Okay. Yeah, I believe that there is one slight mistake over here. There shouldn't be, I'm not going to put absolute values over here just yet. So, yeah, so let's see what happens next. Okay. So after this, notice that in this step right over here, this is the summation from n equals 1 to p of ace of alpha n. And this small p is of course greater than or equal to capital P by assumption, which is greater than or equal to r. And the way we chose this p was that from in the series, ace of alpha 1 all the way up to ace of alpha p, the first r terms appeared in the sequence. So that is how we chose this capital P to begin with. So what's going to happen is that when we're actually summing these terms up, when we are summing the summation from n equals 1 to infinity of ace of alpha n, and then subtracting the summation from n equals 1 to r of ace of alpha of ace of n, the first r terms are going to cancel out, because the first r terms are over here and the first r terms are also over here. So the first r terms are going to be cancelled out, and then we are only going to be left with a finitely many extra terms. And by the triangular inequality, those finitely many extra terms had to be less than or equal to the summation from n equals r plus 1 to infinity of the absolute value of ace of n. And similarly over here, this is just, if you just subtract this off, because s is the actual sum, you're going to get the summation from n equals r plus 1 to infinity of ace of n in absolute value, because, well, this is just s, and then you're subtracting off the first r terms from the sum, so you're just going to be left with this. But then by the triangular inequality, this part is also less than or equal to the summation from n equals r plus 1 of infinity of the absolute value of ace of n. So I'm just going to write this out again. I'm going to say this also has to be less than the summation from n equals r plus 1 to infinity of the absolute value of ace of n. But now if you remember, we established that this entire thing has to be less than epsilon over 2, where epsilon is any positive real number, which is equal to epsilon. So what I get by this, by this long chain of inequality is that the summation from n equals 1 to p of ace of alpha n minus s has to be less than epsilon, which if you expand, we'll get that s minus epsilon has to be less than the summation from n equals 1 to infinity of ace of alpha n, which has to be less than s plus epsilon. And now if you take the limit as p approaches infinity on all three sides, you're going to get that s minus epsilon. So this has to be p. And now you take the limit as p approaches infinity, you're going to get ace of alpha n has to be less than s plus epsilon. And now you're almost done. Since this is true for any epsilon greater than 0, what you can conclude is that this implies that n equals 1 to infinity of ace of alpha n. To be more precise, you could say that this is true by the squeeze theorem. But I mean, you can just general say that since this is true for any epsilon greater than 0, this must be true that the summation from n equals 1 to infinity of ace of alpha n is equal to s. Just to give you a little bit more idea about how we go from this step to this step, is let's say that you have that something agrees to this inequality, that 10 minus epsilon is less than x, which is less than 10 plus epsilon. But the important thing is that this is true for any epsilon greater than 0. So I mean, it's true for 1, it's true for 0.1, it's true for 0.00001, it's true for 1 divided by a trillion. And so in general, the only thing, one thing, this has to be less than or equal to. All of these are less than or equal to signs. So yeah, so then that means that x has to be equal to 10, right? So that's the only one. It's the only thing that will satisfy this inequality or this chain of inequality. So you could say that by the squeeze theorem, the summation from n equals 1 to infinity of ace of alpha n has to be equal to s. And yeah, that will complete the proof. So essentially what we have shown by the end of this proof is that no matter in what order, oh, by the way, this also has to be less than or equal to, that no matter in what order you sum up the terms, you are always going to get the same result. You're always going to get that the summation from n equals 1 to infinity of ace of alpha n, where alpha is any rearrangement, any permutation of the set of natural numbers, is going to be equal to s. And yep, that completes the proof. In the next video, I'll show you the proof. I'll show you the second part of the theorem, second part of the Riemann's rearrangement theorem. And I'll show you a proof for part 2, which in my opinion is the more interesting of the two parts.